We're going to take a look at problems 3, 4, 5, and 6 in our Newton's Laws practice problems. They all refer to the mystery box. So this is a picture of the mystery box. Before I was in room C209 at the high school, I used to be one floor up in room C309. And a couple years into my stay here at the high school, they decided to move me down one floor. So I packed up all my materials in June, moved it into C209. And when I left for the summer and I came back, there was this box that's just sitting there and it's locked. And I have no idea what's inside of it. Maybe my fortune's inside it. Maybe one day when I retire, I'll invite you all back and we'll crack it open. We'll see what's inside. But for now, it's just the mystery box that sits in our room. And I did take the mass of it. Its mass is 8.5 kilograms. All right, so let's take a look at problem 3. The mystery box is sitting still on a flat table. Mass is given. So before we do anything with the free body diagram, we want to write some information off to the side, specifically velocity, acceleration, and net force. The box is just sitting there, so its velocity is 0. It's not changing what it's doing, so the acceleration is 0. And from sigma f equals ma, if the acceleration equals 0, that means the net force, or sigma f, equals 0 as well. Alright, so we have that all off to the side. Next step is to assign a positive direction, and the forces we'll be looking at are vertical ones, so we'll either pick up or down. I'm going to arbitrarily call up the positive direction, but down as positive is just as good because there's no preferred direction in this particular problem. Now we can go to the actual free body diagram, drawing the forces. And the force we always want to start off with is the force of gravity, also known as weight. And which way does it point? Straight down. So we're going to go ahead and draw that straight down. There's mg. There's all sorts of ways to write force of gravity. It could be F sub g or w. I'm going to stick with mg because it reminds you how to find the force of gravity. Just multiply the mass times the acceleration due to gravity. And you never have to show any work in doing so. Just go ahead and crunch the numbers. The mass is given to 2 sig figs. You should be able to get 83 newtons. Good, so you just label it right there on the free body diagram. It says the problem involves normal force. How do we know there's a normal force? Well, because there's a surface. Anytime there's a surface involved, there will be a normal force. The 8.5 kilogram mystery box is pressing on the surface. The surface responds with a normal force perpendicular to the surface, in which case that's going to point up. So there is our normal force. Now, we could go through the whole sigma f equals ma business and list the forces with their proper signs, but let's just see what's happening. We can see the net force equals 0. Now, let's remind ourselves, net force, sigma f, is the combination of all forces. What are the forces? Well, you have mg down and n pointing up, and if the net force, the combination, has to be 0, I hope you can convince yourself that in magnitude, the normal force has to match the magnitude of the weight. The normal force in this case is just supporting the weight. So we can see the normal force is going to be 83 newtons. The normal force from the table is just making sure the mystery box doesn't fall, making the net force 0. Let's go on to number 4. So there's our mystery box again, and this time we're pushing down with an extra 15 newtons of force, but it doesn't say it's going anywhere, so once again we can say that the velocity, the acceleration, and the net force are all 0. Just list it off to the side. We'll assign a positive direction, and once again I'm just going to call up the positive direction for no particular reason, just because, I don't know, I arbitrarily chose that. If you want to call down positive, you're going to get to the same answer, no problem. We're going to go ahead and start putting the forces on the free body diagram, starting with weight, and it's the same mystery box, so it still weighs 83 newtons. In fact, I want you to try to draw the length of the weight vector the same in number 4 as you did in number 3 to really show this fact that it's still the same mystery box, it still weighs the same amount. We are pushing down with an extra 15 newtons, so let's just draw that, and I'm going to use just the generic symbol F for that, because we don't know what kind of force this is, it's not given as a special type, you're just pushing down, so it's just the generic force. And then there's going to be a normal force because there's a surface. Normal force is going to point up, so let's go ahead and draw that. Now, here I've drawn normal force equal to the size of the weight vector, but let's just think about that for a second. If in total down is 83 newtons and extra 15 newtons, well then there's no way the normal force could only be 83 newtons. The normal force certainly cannot be the same as the weight as it was in problem 3, because then there'd be more force down than there is up, and then the net force would not be 0. So how much will the normal force be? Well, I'm not really sure just yet, but I do know it has to be larger than 83 newtons. So let's go ahead and draw it larger than 83 to really reflect that. So now what we're going to do is we're going to list all the forces with their proper signs. So we know that we have n pointing up, and up is positive, so it's positive n. We have force pointing down, and up is positive, so it's negative f. And mg is pointing down, so that's going to be minus mg, and they have to add up to 0. So here's all the forces combined, adding up to a 0 Newton net force. Let's go ahead and do our algebra, solve for, in this case, normal force by moving force and mg over to the right-hand side. So we can see normal force has to be F plus mg, which hopefully your gut is sort of telling you that in this case normal force has to make up for all this force pointing down. You put the numbers together, you should have no problem proving to yourself that normal force in this case is 98 newtons. So in some cases, normal force is equal to weight, but in other cases, normal force is not. The normal force is a reaction force. It will react to whatever you're doing. So if it's only the force of gravity, only the object's weight pushing on the surface, well, normal force will just support that. If you apply extra force down, normal force will respond with more force up to make sure that the net force is 0. So what do you suppose would happen if I push up with 15 newtons, or some force that's pointing up? Well, in this case, we're sort of relieving pressure off the surface. Normal force would be reduced by that amount. So in that case, it would be mg minus F to get a normal force. That would just be enough to support the object so that the net force equals 0. So the normal force, again, will respond to whatever it is you're doing in that vertical dimension. All right, let's go on to number 5 here. It's a little more complicated. Go ahead and, at this point, maybe pause the video, write information off to the side, start to build up the 3x diagram all on your own, then come back to the video to see how I do it. Okay, so in this case, we are pulling it from rest along a frictionless surface. So that means it's going to be moving to the left. And so now it's in motion. We're going to call the initial direction of motion the positive. That's our usual way of doing it. It's a frictionless surface, meaning there's nothing opposing the force pulling it, which means that pulling it to the left, it's going to accelerate to the left. And from sigma F equals ma, which is a vector equation, the direction of the net force is the direction of the acceleration, and so the net force is going to point to the left as well. Now remember, we're not putting any of these vectors on the free body diagram because not a single one of them is a force. Forces are always measured in newtons. Velocity is measured in meters per second. It's not a force. Acceleration is measured in meters per second squared. It's not a force. Now, sigma F is measured in newtons, but remember, it is not a force. It's the combination of forces. It's what you get when you put all the forces together. So sigma F not being a single force, it does not go on the free body diagram. It will never go on the free body diagram. So for the free body diagram, we're going to draw the actual forces, and, well, it's the same mystery box, so it's going to have weight of 83 newtons pointing down, and it's sitting on this flat surface, and there's no other forces vertically, so hopefully you should be able to convince yourself that the normal force will, just like in problem 3, be 83 newtons. In the vertical dimension, there's nothing else happening. It's not accelerating vertically, and there's no other forces like in number 4, so the normal force is just doing its job of supporting the object's weight. But we do have a string pulling it with a force of 24 newtons to the left. What kind of force is in a string? Hopefully you drew this as a tension force. Because if there's a string, there's going to be a tension, and strings always pull. So if the string is on the left-hand side, the string is pulling to the left, and it gives us a magnitude of 24 newtons. By the way, now is a good time to mention that notice at no point do I only put the number, the amount of the force. I always list what kind of force it is, and when I don't know what the magnitude is, I put the kind of force all by itself. And that's how we do these free body diagrams. You never just put, for example, 83 newtons. You have to write mg equals 83 newtons. I don't just write 24 newtons. I put T equals 24 newtons. So at the very least, you have to say what kind of force is being represented by each of these force vectors. And then if you happen to know the magnitude, you put that as well. Okay, so in this problem, we're going to find the net force and the acceleration. Well, in the vertical dimension, hopefully you should be able to see that 83 down, 83 up, they cancel. And remember, motion in one dimension is independent of motion in other dimensions. So in the vertical dimension, there is no net force. But horizontally, well, there's nothing pulling back to the right. There's only the force to the left. So in this case, the net force, since these two cancel, is just the tension force, and it's pointing to the left. So we can say that sigma F equals positive 24 newtons. Now we also want to find the acceleration. What do we do for that? We're going to use sigma F equals ma to go ahead and rearrange it for acceleration. We have sigma F, we have the mass. Let's go ahead and find the magnitude and direction for the acceleration. So A equals sigma F over m. We're going to do positive 24 divided by 8.5. And we should be able to get positive 2.8 meters per second squared, or 2.8 meters per second squared to the left. Words are fine. You know, I always like to use the sign as the direction. Since we assign a positive direction, you can go ahead and put that positive sign on there, but make sure you do it. It's not implied. If you just write 2.8 meters per second squared, you would not get credit for giving direction because you didn't actually put the plus sign or the words to the left. Let's go ahead to number 6, and once again, I want you to pause the video, try to do it all on your own, then come back to see how I solve it. Alright, so there's our 8.5 kilogram mystery box. It says we're pulling it to the left, so we know it's going to be moving to the left. Ooh, but look at that phrase that's underlined. It says moving at a constant velocity. That phrase should really jump out at you, not only because I underline it, but also because that carries with it a lot of meaning. If it's moving with a constant velocity, that means it's not speeding up, it's not changing direction, It's not slowing down. So what is it not doing? Well, hopefully you didn't say not moving, because it says it's moving, right? We know it's moving to the left, but it's not accelerating, which means the acceleration equals 0. Oh, so we're already halfway done with this problem. We know the acceleration. It's 0. Done. So wait a second. By sigma f equals ma, if the acceleration is 0, that means the net force must be 0. Oh, we're completely done with this problem. Although, we should still draw the free body diagram. So yes, we've mathematically answered the problem here, but we should be able to visualize this. So let's go ahead and draw the free body diagram, starting, of course, with weight pointing straight down, and it still weighs 83 newtons, so, still try to draw the weight vector the same. And there's nothing else happening vertically, so we know the normal force is going to be 83 newtons as well, and it's still being pulled to the left by that tension in the string of 24 newtons. So, wait a second, what is different about this problem from number 5? Well, in number 5, the box was accelerating, but in number 6, it's not. In number 5, there was a net force, but we know that since it's not accelerating in number 6, the net force has to be 0, which means this free body diagram can't possibly be complete. There's got to be something else there so that the net force is 0, as opposed to being 24 newtons. So which way must this other force be pointing? Well, if the tension is pointing to the left and the net force has to be to the right, has to be 0, the other force has to point to the right. It has to be. Something's got to point to the right so that it'll cancel out this tension force to the left. So what sort of force might this be? Well, the clue is in the problem. It says it's pulled along a rough surface, as opposed to number 5. So hopefully you can see that the missing force here has to be a force of friction, which we symbolize with F sub F. And how much must that force of friction be? Hopefully you've convinced yourself that if the net force equals 0 and there's 24 newtons to the left, that means the friction force had better be 24 newtons to the right. And now we have a complete free body diagram that shows it's moving to the left, but it's not speeding up, slowing down, or changing direction. So the acceleration is 0, the net force is 0. So it's still moving to the left, but the forces are balanced. None of these forces is winning over the other. This is the situation known as equilibrium.